Continuing on with colligative properties, we're going to discuss the freezing point depression constant and the boiling point elevation constant. The derivation of these two constants are the same, except for there's going to be a difference of where we insert two values, and there's also going to be a minus sign. So we're going to start with the freezing point depression constant. So our solvent has a mole fraction which is approximately 1, approaching 1, getting very close to 1. And we know that freezing occurs whenever we have the chemical potential of two phases, the solid and liquid phase, which are equal to one another. So at the temperature of fusion, the freezing temperature, chemical potential of our solid solvent equals chemical potential of the liquid at that same temperature. Okay, and we can substitute in, this isn't going to be exactly the chemical potential of the liquid, it's going to be the chemical potential of the solution. So we have mu1s at the temperature of fusion is equal to mu1 of the liquid plus RT log activity of the solvent. Okay, so our rearranging this for the natural log of the activity, just algebraic rearrangement here, log of A1 is going to equal chemical potential of solid minus chemical potential of liquid divided by RT. Okay, now we're going to use the Gibbs Helmholtz equation and make a nice substitution, which is going to help us out. So Gibbs Helmholtz equation says that the partial derivative of our molar Gibbs energy of our solvent divided by temperature, that quantity, its partial derivative with respect to temperature at constant pressure and mole fraction, that is equal to, I haven't substituted anything on this next line here, that's just chemical potential, reminding ourselves that chemical potential is just the molar Gibbs energy of that component in that phase. Next one. And according to the Gibbs-Helmholtz equation, this is the negative molar enthalpy of the solvent divided by temperature squared. Okay, so if we substitute that in here, you have mu1s over RT minus mu1L over RT. So each of those is going to be their respective negative molar enthalpies divided by RT squared when we do that substitution. All right, so writing that now, we have derivative of the log of our activity coefficient with respect to temperature, and that's also a function of pressure and mole fraction, which we're keeping constant, is equal to, substituting in and taking account of the negative sign, molar enthalpy of the liquid of the solvent minus molar enthalpy of the solid solvent divided by RT squared. And then the difference in the molar enthalpy of the liquid and molar enthalpy of the solid is the enthalpy of fusion. And the molar enthalpy of fusion. Got to stick that fuse right in there. Okay, molar enthalpy of fusion for our solvent divided by RT squared. Okay, and then this is the derivative with respect to temperature. So if we want to get this at a specific value of temperature, we're going to multiply both sides by dt here and then integrate. So what we're going to get then is the log of the activity is equal to the integral from the temperature of fusion of the pure liquid, T fuse star is the enthalpy, is the freezing point at that temperature and pressure for that pure solvent of the pure liquid, integrated up to the new melting point, the new temperature of fusion. And that's this quantity here is our integrand, delta fuse, molar enthalpy of fusion for our solvent, divided by RT squared, integrated with respect to temperature. Okay, now we're going to take our favorite Taylor series of the chapter, that the natural log of the activity of the solvent, which is at very high mole fraction approximately equal to its mole fraction, which is equal to the natural log of the mole fraction of 1 minus chi2, because chi1 plus chi2 equals 1. Sum of mole fractions is 1. And then taking the first order Taylor series of ln 1 minus x gives you minus x. So this is going to be approximately, taking the Taylor series, minus chi2. All right, so we have minus chi2 is going to equal this integral here. So that's equal to minus chi2. All right, we're going to make a few other assumptions here. We're going to assume that this enthalpy, molar enthalpy of fusion, is independent of temperature, at least over this very small range. This will usually only be a few degrees, so that's a pretty reasonable assumption. So that's going to get us minus chi2 is equal to molar enthalpy of fusion divided by gas constant, also independent of temperature, integral from T fuse star to T fuse, the freezing point of the liquid to freezing point of the solution of dt over t squared. All right, so if we move this minus sign over and then fulfill that integral, complete that, should be able to convince yourself through that calculus that we're going to end up with chi2 equals delta fuse h bar, molar enthalpy of fusion. I'm going to stick that 1 up here as well, just so we're clear, divided by gas constant times 1 over melting point minus melting point of the pure liquid. Solution, liquid. Okay, and we know that if we have a very dilute solution, for a very dilute solution, we're going to have that the mole fraction is approximately equal to the molar mass of the solute times the molality of molar mass of the solvent times the molality of the solute if it is very dilute. So we can substitute in here the molality, the molar mass of the solvent times the molality of the solute, and that will give us the equation, and also multiplying the top and bottom of here by T fuse star over here and T fuse top and bottom over here. We're going to get molar mass of solvent times molality of solute equals molar enthalpy of fusion of the solvent divided by gas constant times freezing point of liquid minus freezing point of solution divided by freezing point of solution, freezing point of liquid times freezing point of solution. Okay, so two more approximations. Another approximation we can make here. We know that T fuse star is approximately equal to T fuse. This change in the temperature is going to be very, very small. So the freezing point of the liquid is going to be very similar to the freezing point of the solution, especially relative to their difference. And we're going to define the quantity delta T fuse is going to be defined as T fuse minus T fuse star. So that's going to give us the expression down here, which is going to be that we're going to have big M1 times M2, molar mass times molality, molar mass of solvent times molality of solute, equals minus enthalpy of fusion for the solvent divided by gas constant times, this became a minus here when we pulled this out, times delta T fuse divided by, these are approximately equal, so we set them both equal to T fuse star squared. Now we know that we have the empirical expression that delta T fuse equals minus Kf times M2. We have what we call the freezing point depression constant. So we have Kf is the freezing point depression constant. So comparing terms here, if we divide both sides here by the molar mass of the solvent, what we're left with, or if we say isolate this delta T fuse here, we'd have to multiply both sides by gas constant and by the freezing point of the liquid squared, and then divide both sides by the molar enthalpy of fusion. Then we have the expression that delta T fuse is going to be equal to molar mass of the solvent times gas constant times freezing point of the pure liquid squared divided by molar enthalpy of fusion of the solvent. And then this is all times the molality of the solute. So we can see from this correspondence here to our empirical expression, delta T equals minus Km, delta T equals a bunch of stuff times M. So our freezing point depression constant, Kf, is finally going to be molar mass of the solvent times gas constant, that is a terrible R, times gas constant times the freezing point of our liquid squared divided by its enthalpy of fusion. Sorry, forgot to carry on minus sign. There's going to be a minus sign there. Divided by enthalpy of fusion. And this is our final result. Okay, so we see that it depends on what the molar mass of the solvent is. It depends on what the freezing point of that liquid is. And it depends on how much heat it takes to go from the solid to the liquid, what its enthalpy, molar enthalpy of fusion is. If we wanted to get this for the boiling point elevation constant, we would make only the we would only need to make the following replacements. Instead of mu s here, instead of the solid being the chemical potential here, going from the liquid to the gas would be mu of gas, so chemical potential of the gas. So up here we would have the enthalpy, the molar enthalpy of the gas minus molar enthalpy of liquid minus molar enthalpy of gas. And that would be the negative enthalpy of vaporization, negative molar enthalpy of vaporization. So that gives us a minus sign, and instead of delta fuse H bar, that would be delta vap H bar. And then carrying that through, and then instead of integrating from the melting point of the liquid to the melting point of the solution, we'd integrate from the boiling point of the liquid to the boiling point of the solution. So through all of that correspondence, we can make the following claim about the boiling point elevation constant, that Kb is also molar mass of the solvent times gas constant times the boiling point of the pure liquid solvent divided by the enthalpy, the molar enthalpy of vaporization of the solvent. So generally, the freezing point depression constant is bigger than the boiling point depression constant. So generally, Kf is greater than Kb. And we have the empirical relation again for boiling point. That's a bad color to use there. Let's use blue. Delta T VAP equals Kb M2. So the molar enthalpy of vaporization is usually bigger than the molar enthalpy of fusion, this temperature is usually bigger than this temperature, but due to these ratios, this relative to this is much bigger than this relative to this. So what ends up happening is you're dividing by a larger number for your enthalpy of vaporization. For example, for water, this is about 40 kilojoules per mole, and for water, this is about 6 kilojoules per mole. So this is about 7 times bigger for water, whereas this is only about a factor of, say, 1.3 bigger for water. So that's why water has a much bigger Kf than it does Kb, and that is generally true due to the differences in enthalpy of vaporization and enthalpy of fusion.